audio, start video. Okay. I wonder if we have Nicholas. We have Nicholas with us. Yes. And let's see if we got anybody else. Nope. Nicholas, it's just you and me right now. Oh, no, no. We got Phoebe. We got Nicholas and Phoebe. But that's all for right now. Got Nicholas and Phoebe. But it's we're still early. Hey, we got 3 minutes, 2.5 minutes before class is going to start. Do you guys have any questions for me before we get rolling here? Here's your chance to get some free knowledge here.
What was the free knowledge about? I must have missed something.
Well, see, you pay for the class, right? And the class doesn't start till 5:30, and so anything before then, you didn't have to pay for it. It's extra. It's free. Gratis en español. Es gratis. Well, you guys don't have any questions for me. I'm waiting for the others.
I actually do have a question.
Yeah, go
I
ahead.
don't know if this has been asked already, but do we also get to make a formula sheet for this time?
Yeah, oh, absolutely. Every time. One page, 8.5 by 11. Notebook page on one side. You can write down anything you want. All the equations, poetry, whatever makes you happy. That'd be good. I'll have a little bit of review tonight. You all know that there's a test Thursday night at 5:30 in the lab. And it's over chapters, I wrote that down someplace, 8, 9, and 10. Your test, your exam, Thursday, 5:30 in the lab. See, we're not having a lab that night. You're just going to take your test. You'll have plenty of time. You can take the whole 3 hours if you want. And it's on chapters 8, 9, and 10. And we'll have a little bit of review here, but mostly tonight's going to be on this chapter 10. Anybody else, comment or question? Class is starting officially in 5, 4, 3, 2, 1. Bingo, class has started. Now you can still ask me something if you want. Do you have any questions about anything? Well, let's see who we got on board here. Oh, look at here. We got Nicholas, Phoebe, Daniel, Christy, Chastity, and another excellent student down here that's off my page somehow. I don't know how this thing works. I can't figure out who that is. I could use process. Oh, there's Zach. I've got Zach. Yeah, Daniel. I got Daniel. Can't think of who that other wonderful student is. Let me look at my rule book here. It's a small class. I like small classes. Let's see here. How about, it might be Jacob or Brian or Stephen. I don't know. We'll figure it out. Okay, well, let's get started here. Let's do some problems together. That'd be good. I think I've given you all the theory. Let me see. Well, no, let me double check and see if there's any theory in chapter 10 that I missed out on here. No, I think we have covered all of the theory in all of these chapters. You might be rusty on this internal resistance of batteries. We probably should do that. Well, here, let's work some problems, and we'll try to help you on your test too. Okay, now this first one I want to do is 1051. Help me find it. 1051. They said the duration of a photographic flash is related to an RC time constant, which is 0.1 microfarads. Well, that's a screw up. Guys, time is not measured in farads. Here's what they meant. The book made a mistake. The time constant is, there's this little symbol called tau, and it's equal to R times C. And they gave it to us, and they said it's 0.100 micro, and up to that point they were okay. But see, time isn't measured in farads, it's measured in seconds. So the book had microfarads. That's wrong. I'll put an unhappy face there. And this is correct. The book had microfarads. This book isn't perfect. I don't know if you've noticed, but I really like the price. How about you guys? Do you like the price?
Yes.
Yeah, you like the price. Let me ask, is Stephen on board? Hey, Stephen, if you're on board, speak up. Stephen? How about, let me keep trying here. How about Brian? Brian, are you on board? Speak up. Okay, Jacob. Jacob, are you with us? If so, speak up, Jacob. I still don't know who my mystery person is down here at the bottom.
Did you get Daniel?
Daniel's here. I know he's here. But let me ask Daniel. Daniel, do you like the price of the book?
Yeah.
What is the price of the book, Daniel?
Free.
Yeah, it's free. It's free.
Sorry, I'm just trying to help figure out who your mystery person is too.
Yeah, I am too. I'd love to know who it is. Well, we'll figure it out eventually. Okay, now let me continue with my problem. We're going to do this problem. It says here, the resistance of the flash lamp is 0.04 ohms. Let me write that down. The resistance is 0.04 ohms. During discharge, what is the size of the capacitor supplying its energy? Okay, now look, guys, they've given you this, and they've given you this, and all we got to do is push buttons on our calculator and get the capacitance. So do it. Here's R. Here's tau. That's a Greek letter tau. It's T-A-U, tau. Put 0.1 in there and solve for the capacitance. On your mark, get set, go, and we'll see what it is. Now watch it. That's a microsecond, though. I don't want to forget that. Okay, I've got my value for the capacitance. And let me ask my friend Zach, unmodulate, that's the wrong word, unmute. Yeah, that's it. Zach, unmute.
I haven't worked it yet, but yeah, I'm getting there. I've had an issue trying to find the page on the book, but I'm working on it.
I can't quite hear you, Zach. Can you turn up your volume? Is that possible?
No, but
I wonder if I can turn my volume up. I don't know how. Anyway, I can barely hear you, Zach. What'd you get for the capacitance?
I haven't typed it yet.
Okay, that's okay. Take your time. Here, I'll write it out for you guys. 0.1 microseconds is equal to 0.04 ohms times C. Okay, now put that in your calculator. And, oh, that's Jacob. It's Jacob that I couldn't figure out who was missing. Hey, Jacob, unmute and say hello, please, Jacob.
Hello.
Hello. Jacob, what'd you get for the capacitance?
I haven't done it yet. I just got here, so I'm writing
No,
stuff
that's
down.
okay. That's fine. We'll pick on Daniel. Daniel, unmute and say hi.
Hello.
Yeah, Daniel, what'd you get for the capacitance?
Is it 2.5?
Yeah, but 2.5 what?
Micro. Hold on.
Yeah, you're so far so good.
I'll say I know micro.
Yep,
Micro.
you're doing great. It's
Not
2.5 micro what?
Is it coulombs?
No. Capacitance is not measured in coulombs. Charge is, but we're not doing charge. We're doing capacitance.
Is it farad?
It's farads. Here we go. Here's the answer. 2.5 microfarads. Now let's see how we did. Go to the back and look up the answer for 1051, and we'll see what the answer book says. They said 2.5 microfarads. Yay, we got it right. Now, they have two answers. They must be asking us something else. Let's read on and see what else there was there. Okay, B, part B. What is the time constant for charging the capacitor if the charging resistor is 800 kilo ohms? Okay, let's do that. They're asking us another question now. They want to find tau equals RC, only this time the R is 800 kilo ohms. And see, the C we figured out, it's the 2.5 microfarads. Okay, go ahead and figure that out. I'll do it too, and we'll see what we get. Go ahead. Take 800 kilo ohms times 2.5 microfarads and tell me what you got. And I'm going to ask, I think I'm going to ask my friend Christy. Christy, what'd you get for the time constant? Earth calling Christy. Earth calling Christy.
Can you hear me?
Yeah, I can hear you. Very good.
Okay, sorry, my mic messed up, but I got 2 seconds.
That's exactly right. 2 seconds is the answer. And that's the answer they have in the back. Well, good. We just did a time constant problem. Any last words, comments on that one before we move on? Okay, let's move on. Okay, now this next one I wanted to do was 1057. Let me make a little room here. If you guys are happy, I'm going to erase that one. We just did problem 1051. While I got that up there, let me show you, if I ask you for a dimensional analysis on that equation, here's what I want. Let me show you what I want. See this here, you always start with the units, the customary units. This is a time constant. The customary unit for time is seconds. This is resistance. The customary unit for resistance is ohms. This is capacitance. The customary unit for capacitance is farads. Now, what you don't do, what drives me crazy, is the students that go to this Appendix A. I'm going to show you what I don't want you to do. In Appendix A, in the very back of your book, they have fundamental units. These are not customary, they're fundamental units. And capacitance, even though they do say it's in farads, they have capacitance as amp squared seconds to the 4th kilogram meter squared. Now, what that is correct. Those are what they call fundamental units. And a resistance, for resistance, they have kilogram meters squared divided by amp squared seconds cubed. You'll find this in the Appendix A. I do not want you to do this. It's in the back of your book. Now, if you went through here and got rid of all the stuff that you can cancel out, can you see that you'll be left with seconds to the 4th divided by seconds cubed, and it by Jove, it is equal to a second. But don't do it that way. I want you to use customary units. See, these are what they call fundamental units. I might have told you this before, but there are only 7 fundamental units, no matter which unit system you're using. there are four different unit systems. We use the American customary and the System International, which some people call the metric system. The other two are the CGS, centimeters, grams, seconds, and there's a fourth system. They have foot pounds, they have poundals. Never mind. But no matter what system you're using, there are only 7 fundamental units. Anything that can be measured in the universe can be expressed in one or more of those 7 fundamental units, which I find to be rather fascinating, because if you study the Bible, you'll discover 7 all over the place. It's the number for God. Now, I'm probably getting in trouble now, but see, if God created everything and his favorite number is 7, he only needed 7 fundamental units. There you go.
You don't want us to use it.
Say that again, please.
And you don't want us to use them, is what you're saying.
I want you to use customary units. See, because this will drive me crazy. When students use that Appendix A, it drives me nuts. Now, here's what I want you to do. I want you to write that ohms as a volt over an amp, because that's our old buddy V equals IR. You know how that goes. V equals IR. Volts is equal to amps times ohms. So ohms is equal to volts over amps. And farads, the customary unit for farad is a coulomb per volt. Remember, that's what capacitance is. It's defined as charge per volt. And so look at here, the volts cancel out, and you're left with coulombs per amp. And you know what an amp is? It's a coulomb per second. So when you get all through, guess what you get? You get seconds. That's how I wish you guys would do your dimensional analysis in what I call customary units. Okay, well, let's work another problem. That was fun. Any question on any of that? Okay, well, good. That a tad bit of review right there, in case you have a what do they call a dimensional analysis problem on your test Thursday night. All right, this is problem 1057. We're just going to work some problems, and we'll have some little theory sessions now and then. But let me find it, 1057. Okay, I see it here. This is in the book. It happens to be on page 490 in my book. And we do like the price of that book. I don't think they made a mistake on this problem. Let me see if I can get that picture of me off of there. Yeah. Okay, it says, if you wish to take a picture of a bullet traveling 500 meters a second. Here, let me draw you a picture. Here's a bullet, and it's going 500 meters a second. Then a very brief flash of light produced by a RC discharge through a flash tube can limit blurring. Assuming 1 millimeter of motion, this thing is going to move 1 teeny tiny millimeter. Now we need to figure out the time involved in that. You know how that goes. Distance is equal to velocity times the time. Now we have the velocity and we have the distance, and we can figure the time. Now wait a minute, that's 1 millimeter, not 1 meter. The distance is 0.001 meter. The velocity is 500 meters a second. So what's the time for a bullet to go 1 millimeter? Go ahead and work that out, and I'll ask one of my very best students here in just a minute. Okay, well, I got it. Let's ask my friend Daniel, unmute and say hello, please.
Hello.
Hey, Daniel, do you have that time yet on how long it takes for that bullet to go 1 millimeter?
I think it's going to be 2 times 10 to the negative 6.
Very
Second.
good. In other words, 2 microseconds. 2 microseconds. Okay, good. Now let's keep reading here. We're doing problem 1057. If you wish to take a picture of a bullet, okay, a very brief flash of light, assuming 1 millimeter of motion, okay, during 1 RC time constant is acceptable. And given that the flash is driven by a 600 microfarad capacitor. Now let me write that down. The capacitor is 600 microfarads. Okay. What's the resistance in the flash tube? Well, here's the equation. Tau equals RC. Now we know the tau, it's the 2 microseconds. And we know the C. What does it mean in this class when I circle something? When
You're
I
trying to
circle
figure out
something in
what
this
it
class,
is.
it means we know what it is. See, we got the tau, it's 2 microseconds. We got the C, it's 600 microfarads. So now we're going to find the resistance. Go ahead, I'll shut up. Find the resistance you need for this flash camera. Well, I got what I think it is. Let me call on. Let's see. I already picked on Christy. How about Chastity? Hey, Chastity, what do you have that resistance for me, Chastity?
3.3 times 10 to the negative 3.
That's it. You got it. What Chastity said was 3.3 times 10 to the minus 3. Now, what's the units on that, Chastity?
Micro ohms.
Say that again, please.
Micro ohms.
No, it's not micro ohms. It's just ohms.
Oh, okay.
It's just ohms. Now, if you wanted to, you could say 3.33 milliohms. But you're not confused, are you, Chastity? You're okay?
I'm okay.
She's okay. All right, well, let's see how we did on that. Go to the back there and look up the answer to 1057, and we'll see how we did on that. Says here 1057. That's exactly what they said. Yay, we did great. Okay, well, let's do some others then. All right. If you're all happy, I'm going to erase this. We're going to do a different problem. This is just going to be one I made up. It's not in your book. But now's your chance if you have anything to say. All right. Now we've studied this business about RC time constants. We've studied this business about tau equals RC. We did an experiment on it. Let me see which experiment that was. You came to lab and we did an experiment. It was our fourth lab. It was experiment 11. It was called capacitive discharge. We did a whole lab experiment on this. So this is not something new and strange to us. And plus it's in this chapter. It's in chapter 10. Okay, so let me draw this circuit here. We'll put a 6-volt battery here. We have those in the lab. And we have a 1 kilo ohm resistor. We have those in the lab. We'll have a switch here. Our switch could really just be unplugging the power supply like we've done before. And right now, this is a 2 microfarad capacitor, and it's uncharged. There's no charge on it at all, but we're going to throw this switch, and charge is going to start leaving. It's going to go in this circuit. Little pluses are going to they're going to go this way. They're going to come through here, and they're going to start filling up this that side of the capacitor, and that will repel pluses from this side. It'll make this side negative, and the little pluses are going this way. We're going to close that switch. There it is. It's closed now. And those little pluses are going to go into the negative terminal of the battery, where all good little pluses want to go. That's where they want to go, to the negative, what they call cathode. Okay. Well, so what? Well, we're going to ask you some questions. The first question is what do you think the initial current is going to be? When you first throw the switch, remember there was no current to start with because the switch was open. But when you throw that switch, what will be the initial current? You think about it, and then I'll ask somebody, and we'll get some opinions on that. We want the initial current. Can you read my writing? That's supposed to say initial. The initial current. Let me just ask some people here. How about my friend? Let's pick on Zach again. He's a good sport. Zach, when you first throw that switch, What do you think the initial current's going to be?
Was it? Nope, I got V equals hour. Hold on, let me.
Zach, I can barely hear you.
I did the wrong math. V equals R. Six divided by 1,000. So
Yes.
0.006.
Yes, very good. The initial current is going to be 0.006. Now, what are the units, Zach?
Amps.
Yeah, good going. Now let me draw you a graph of that so that you'll understand. See, if you plot up the current versus time, it's what they call an exponential decay. It starts off right here, like Zach figured out, at 0.006 amperes. And then it drops off like that. It's called an exponential decay. Now, the reason why it drops off is as this capacitor fills up with pluses. See, pluses are coming in here, and pluses are filling up this plate of the capacitor. And here comes some little pluses. Here they come, and they come in here and they say, hey, wait a minute. That thing's got a bunch of pluses in there already. I don't want to go there that much. But the battery says you're going there whether you like it or not. So a few more pluses are added to this plate. But the next pluses that come along, he's got a bigger problem. There's more pluses than ever. Do you understand? It slows the current down because those pluses repel any pluses that are trying to come in. So you see what happens to the current? It slows down. In fact, there's an equation for it. It goes like this. It's your initial current, which Zach figured out by just taking the voltage and dividing by the resistance. And it's e to the minus t over tau. That's the equation. That's the equation for the current. So here, let's just figure it. What did we say the time constant was? We never did. That's going to be question B. That was question A. I want to figure the time constant now. I'm going to shut up. Now, you know the time constant is R times C. We got the R. There's the R. We got the C. There's the C. Get the time constant. I'll shut up for a tiny minute. Find the time constant. We'll go to one of my friends here. How about Stephen? It's good to see you, Stephen. You're with us. Glad you're aboard. Stephen, have you figured out the time constant yet? Stephen, unmute and say hi, please.
Hello.
Hello. Multiply R times C and tell me what you get.
R times C. C's capacitance R is.
C is 2 microfarads equals 2 times 10 to the negative 6.
0.002.
Yeah, good going. Proud of you. It's
Seconds.
0.002. Now, what are the units, Stephen, for time constant?
Seconds. We just did this, Stephen. You better not miss this.
Okay, seconds. I was in
It's
the bathroom.
seconds. Very good. Now, if
Hello?
you want to be fancy, you can write that as 2 milliseconds. Same thing. Means the same thing. Now, see, that's one time constant. I tell you where that is. It's right
Hello?
in here someplace. It's where you have, you come over here, it's where you have 37% of your starting current. 37%. Now let me show you why. See, this is your starting current. You could call that I sub 0 if you wanted. And this is e to the minus tau over tau. If your time is one time constant, then you have tau divided by tau. Well, that's a -1. Get your calculator out and push in e to the -1 and see what you get. I'm going to do it, e to the -1. You know what I'm getting? I'm getting, well, it's really 0.3679 or something like that times your original. I just rounded it off and called it 37%. You reach 37% in one time constant. That's what your current is after one time constant. Okay. Part C. I'm asking you problems on this. Is there room here? Yeah. Question letter C. I want you to find the current. Find the current after one time constant. When you plug in, what did we say it was? 2 milliseconds. Plug in 2 milliseconds in this equation and solve for it. I'll wait. I want to know what this current is. Go for it. Okay, guys, this here is 6 milliamps, right? And so you take this times 6 milliamps, and here's what I get. I get 2.207 milliamps. That's what this is. At one time constant, you have just round it off to 2.2 maybe, 2.2 milliamps. So you started off with 6 milliamps, but after one time constant, you have 2 milliamps. Okay, that's question C. Now question D, I'm going to ask you, I want to know what the voltage is on the capacitor. Find the voltage on the capacitor after one time constant. Now we know what the time constant is. It's 2 milliseconds. Find the voltage. Do you know how to find voltage on capacitors? And let me refresh your memory here. Is there any room to write any place here? There's a little room up here. Remember, by definition, capacitance is charge per volt. Okay.
I have a question.
Go ahead, I'm listening.
The 0.3679, I got kicked off of the chat for a minute, so I missed something there.
Oh,
So where did
thank
that come
you.
from?
Thank you for speaking up. I want you to take -1 in your calculator and then punch in the little e to the x button. I know you have one, and tell me what comes up. Put in -1 and then hit the E to the X button. And what do you get?
And then put, like, you're saying -1 times e to the -1?
No, you take -1 and you're gonna push a little button that says E to the X.
Right.
And what do you get?
That number,
Yeah,
0.3679.
you get 0.3679, don't you?
Yes.
Okay, that's where it comes from. Now right now, we figured that. We got the current as 2.2 milliamps, but right now we're trying to find the voltage on the capacitor. Does anybody have any ideas on finding the voltage on the capacitor? I'm open to your suggestion. Well, I didn't hear any suggestions, so let me show you a couple of ways to get it. Now, one way is to get the voltage on the resistor. Let's do that. I need a little room here. How would you get the voltage on the resistor? V equals IR. Do we know the current?
I got to get the votes.
Yeah, we know the current. Look here. Here's the current. We know the resistance, so you can get the voltage on the resistor. V equals IR. Ohm's law for resistors. Well, let me call on somebody. What's the voltage on the resistor? We'll call on my friend. We'll pick on Nicholas again. Nicholas, what'd you get for the voltage on the resistor?
Uh, 2.207.
Yeah, that's right. That's right. It's 2.207 volts. Now, I like my voltage in red, so let me put that on here. This voltage is 2.207 volts. And you all know it goes plus, minus. We've learned that, I hope. We've learned that if the current's going to the right, then this side is plus, that side's minus. And so that's the volts. Now to get the volts on the capacitor, it's real easy. Look, you got 6 volts here. You drop 2.2. So what do you got left? 3.8, right? Just call it 2.2. That makes it easy. You got 3. Does that make sense? The 2.2 and the 3.8 add up to 6, right? That's one way to get the voltage on the capacitor. They have to add up to 6. Hey, do you remember Kirchhoff's voltage law? If you go around a loop, going from here to here, it's plus 6. Going from here to here, it's minus 2.2. Going from here to here, it's minus 3.8. If you write all that down, you're back to 0. Here, let me write it for you. Kirchhoff's voltage law says plus 6, going from here to here, minus 2.2. Do I need to show anybody how come that's 2.2? Just speak up if you want me to. I guess you're okay. Don't ever be embarrassed to ask. And then we got a minus 3.8, because this is plus and that's minus 3.8, equals, guess what? It equals 0. Because Kirchhoff's voltage law says the sum of the voltage around a loop is 0. So we can get the voltage on that capacitor like that. But now there's another way. Let me show you another way. Let me make a little room here. If you have one of these on your test, I hope you do well. I bet you'll do okay. The other way is we'll look at the voltage on the capacitor versus time. Now, what's the voltage on the capacitor when you first throw the switch? Remember, there was no charges on it. It was empty. And then they threw that switch. And what will be the voltage on the capacitor when you first throw the switch? Let me ask somebody. Let's see. We'll pick on Stephen again. Stephen, I'll give you a little help here. Q, memorize this. Q equals, C is equal to Q over V. So volts on a capacitor is equal to Q over C. Now remember, when you first throw the switch, there is no charge, there is no Q, it's empty. So what's the voltage on the capacitor, Stephen, when you first throw the switch? What do you think?
Should be 0.
It should be 0. It should be 0. Look here, if this charge is 0, well then the volts will have to be 0. And here's what this graph looks like. It's different than that other graph. It goes kind of like that. Where this is what they call an asymptote. I know you've heard of asymptotes. I'll try to spell it. I'm not sure that I spelled asymptote right. What do you guys think? Did I spell asymptote correctly?
Looks good to me.
Looks right to me.
Did two people say it looks good to me? Well, we're just going to go with it. We can always get a dictionary, I guess. But see, this equation is different than that other equation. This is not an exponential decay. This is a charging capacitor, and the equation goes like this. You know it's eventually going to charge to 6 volts. You could put V max here if you want. That's what this is. This is the maximum voltage. It won't go higher than 6 volts. That makes sense. If you have a 6-volt battery, you're not going to charge that higher than 6 volts. 6 volts is as high as it's going to go. But see, this equation is a little bit different. It goes like this. This is the equation of this voltage in that capacitor. It comes up here and approaches this asymptote, or asymptote, however you pronounce it. Okay, well, let's plug in a 1 time constant and see what we get. We're going to find the voltage on the capacitor at 1 time constant, which we figured out was it was 2 milliseconds, wasn't it? Isn't that what we had a little earlier? I think I erased it. Pretty sure that's right. Is that right? Does anybody take notes in my class? Was it 2 milliseconds?
I think so.
Yeah, I think it's 2 milliseconds. All right. And we're going to find the voltage on the capacitor at 2 milliseconds. And so it's going to be 6 volts times 1 minus e to the minus, well, it's 2 milliseconds over 2 milliseconds. It's just e to the minus 1. Now I'm going to shut up, and I want you to find the voltage at one time constant, which would be, it's right about in here. This is your tau. There it is. There's your time constant. Go ahead. Find the voltage on the capacitor. Using this equation. Plug it in. See what you get. Well, I tell you what I got. I got 3.793 volts. Or you could just round it off to 3.8 volts. We were a little bit sloppy over here. Hey, look, we got the same answer, but a totally different way. We got the 3.8 volts by using this equation here, but we got the 3.8 volts here by just subtracting the 2.2 from the 6. Any comments or questions on any of that? We probably ought to do more of these.
Yeah, I didn't get that answer right. I didn't do something right.
Okay,
Where
here,
did-
let me do it step by step here, Zach. I just need some room here. Thank you for speaking up. Now what we're doing is we got a 6, we got a 1, and we're going to subtract e to the minus 1. Now, if you take minus 1 and push that little e to the x button, that number will be 0.3679, rounded it off there. Now, Zach, do that and tell me what you get.
I got the 3.79.
There you go, 3.79, blah, 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 volts. That's the secret. You have to use that little e to the x button. Are you
Oh, so
okay
what is-
now?
No, okay, so that's what threw me off. What is the 2 milliseconds next to the volts up here?
Now that 2 milliseconds, what that is the time constant. We could solve this at any time whatsoever. This would be 4 milliseconds, 6 milliseconds, etc., etc. It's just that there's a very special time called one time constant.
Right, and that's the 3.79,
Yeah.
3.6. Yeah, all right, cool. I got you.
Okay, now let me ask you one more question here. Let me make a little room here. I need room. Probably should work several of these if we had time. If we had time, we could work a whole bunch until you guys got bored with it. But I want you to find the charge. That's the symbol for charge. You all know that. Find the charge on the capacitor. Use a little symbology there. Find the charge on the capacitor at one time constant, which we discovered was 2 milliseconds. I'm going to shut up and see if you can figure out how to find the charge on the capacitor. Now we found the volts, and we know the capacitance. We even found the current, but I forgot what we did with it, and I forgot what the amount was. Was it 2.207 milliamps? I think it was. We know a lot, but we don't know the charge. So I'm going to shut up and let you think a minute, see if you can find the charge. Well, let me call on somebody and see if they got any ideas on how to find the charge. Hey, Jacob, unmute and say hello.
Hello.
Jacob, do you have any idea how to find the charge on that capacitor?
If I'm being honest, I'm still thinking about it.
That's good. Honesty is worth its weight in gold, Jacob.
I really wish that were true.
Well, we just have to believe it to be true. If you're going into engineering, you want to be honest because
Well,
if
I'm
you
honest
make,
because my
if you
mom
make
told me
some
to be.
mistakes can cost lives. Did you know that?
Oh yeah.
Yeah, it's better to be right up front and say, boss, hate to tell you this, but we measured that thing all wrong. And we forgot to put fuel in the rocket. And so now our astronauts they're going around the moon and they don't have any fuel to get back. Other than that, everything was working good. No, we got to own up to our mistakes and be honest. Okay, well, here, let me give you a little hint here, and then we'll ask somebody else. I want you to memorize this. This is a definition of what capacitance is. Now, those are symbols. Don't get mixed up with the units. See, the units are farads, coulombs, and volts. See how confusing that is? Look, there's a C there and a C there. Those are different C's. That C stands for capacitance. That C stands for coulombs. That's how come I put it in brackets, so I don't get mixed up. But now if you want the charge is going to equal C times V. Can you get from here to here? Can you make it, algebra students? I know you can.
I tried that. I
Good
don't know
for
if I got
you.
the right thing. It's
Well, let's-
7.6 microfarads.
Okay.
No, that's wrong. Microfarads isn't the unit, but it's 7.6 something.
Okay, well, here, let me try it. I don't know the answer yet. We're talking to Phoebe, right?
Yes.
Yeah, Phoebe, okay. Now the capacitance is, let me make a little room here. The capacitance is 2 microfarads, and the volts is 3.8 volts. Hey, I could almost do that in my head. Do you get 7.6 microcoulombs? Phoebe, is that what you got?
Yes, I just had my units wrong.
Well, good. Now you got it. 7.6 microcoulombs. Good going. And here, let me draw you a graph of that while we're at it. As long as we're drawing these wonderful graphs, we'll graph the charge Q versus time, okay? And as long as I got Phoebe on the line here, Phoebe, what do you think the charge is when you first throw the switch? Remember, there's nothing happening. You throw the switch, and what will be the charge at time 0, Phoebe? What do you think?
0.
0, good going. And so this graph looks just like the one for voltage. Now, the reason why is Q equals CV. You can see it from here. And C is just a constant. Remember, the voltage graph looked like that, and it peaked out at 6 volts. But the charge peaks out at 7.6 microcoulombs. Here's your asymptote, and it's 7.6 microcoulombs. And here's the equation. Q equals 7.6 microcoulombs, 1 minus e to the minus t over tau. And now wait a minute, I'm getting mixed up. No. The asymptote is not 7.6 microcoulombs. It's 12. See, it's 2 microfarads times 6 volts. It's 12 microcoulombs. Now let me put the 12 in here. I had it wrong here, but I think it's right now. Now I want us to try this, and at one time constant, what you'll have is e to the minus 1. So take your calculator and put in 12 microcoulombs times that and tell me what you get. Go for it. I'm going to do it and see what I get. I get 7.585 microcoulombs. See, we just rounded off. We got lazy. If you round it off, it's 7.6 microcoulombs. But see, this is the equation for your charge. Okay, well, that was a lot of fun. If we had time, maybe we could do another one of those. Any questions or comments on this charging capacitor problem? Okay, well, let's go back into a previous chapter. So your test is on what, 8, 9, and 10. I think this is, I'm going to give you something in 9, I believe. But I'm going to erase this unless you have a question. Okay, nobody said anything. Now we're going to go back into chapter 9, and we've done problems like this before. Now let's put in a 60-watt light bulb. I think we had those in lab. I think we had some 60-watt light bulbs. And we'll put a 40-watt light bulb here and a 200-watt light bulb here. Now you got to understand something. That's the wattage if they were connected directly to the 110 volts, but they're not. They're in a circuit. And when we get all through, we're going to find the actual wattage of these bulbs, and it won't be what they say on them. I tried to explain that. See, if you get that bulb and look at the top of it, it says 60 watts. But when you put it in a circuit like this, you don't get 60 watts. Now, the first thing we're going to do is we're going to get the resistances. We're going to call this R1, R2, and R3. And I'm going to shut up here for a minute. And you might have forgotten how to do this. But if I ask you how to do this on Thursday night, it'd be nice to get that problem right. I want you to find R1, R2, and R3, and I will shut up for a minute and let you work. You can have a minute and a half. How's that? Go for it. So see if you can get those. Maybe I should remind you and give you a little help. I have a feeling. Does anybody out there need a little help?
I
That'd be
mean, if you're
nice,
trying to
yeah.
hand it out, yeah.
So that's a yes. Some of you might need a little help to get that.
Oh yeah.
Okay, well here, let's give you a little help. Now there's an easy way and a hard way. Now the hard way is to remember that 60 watts is only 60 watts if you're connected directly to the 110 volts. Then you really do get 60 watts. If you're connected directly with nothing else, you get 60 watts. And that's what you get when you plug in a lamp. You're connecting it directly to 110, and it shines nice and bright with a 60 watt light there. And you have these lovely equations. You have one that goes like this. You could use that equation. See, you know what the power is. It's 60 watts. You don't know the current, but you know the voltage. It's 110 volts. So, hey, look at here. You could get the current, couldn't you? Oh, yeah. You could get the current. Now, this is the hard way to do this, but that's okay. It won't hurt us. We're doing it the hard way. I'm doing this now, and I'm getting 0.5454, bunch of numbers, amperes. Well, that didn't answer the resistance. But we have a lovely equation that goes like this. Ohm's law for resistors. And we memorized it, haven't we? Look here, we have the current, we have the voltage, and we can get the resistance. The voltage is 110 volts. The current is 0.5454, blah, 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 blah. And so what's the resistance?
$201.7.
Yeah, that's what I got. This one here is 201.7 ohms. Now you can do that with both of these. You can do the same thing. It just will take you a while, but you could do that. Now that's the hard way. Now here's the easy way. Let's do it the easy way. The easy way is there are 3 equations for power, and one of them goes like this. And see if you connect them direct, like this one here. It's 60 watts. And the volts, we know it's 110. And you have to square it. Hey, look at here, you can solve for the resistance. Do that with me. Let's see what we get. Guess what I get? I get 201 point, bunch of sixes rounded off. Now, which method do you like the best? This way or the way I showed you at first? And that's easier. Okay, now I've given you some help, find these 2 here. I'll be quiet again. Find those 2 there for me, please. Well, I've got these now. I'm thinking this here is 302.5. Did anybody get that? 302.5. Did I do that right? I need an I didn't hear any uh-huhs. Maybe I better. Was that an uh-huh?
Yes.
Yay, good going. I'm double checking here. Yeah,
I'm
that's
not gonna
right.
lie. I'm not exactly sure how to find the R2 and R3 since it's split right there. I don't remember how to do that exactly.
Well, it doesn't matter that they're split. What you have to do is you have to realize that this 40 watts is if it was connected directly to the 110. Here, let me draw it for you. Now, is that Christy? Am I talking to Christy?
Yeah.
Yeah, I'm talking to Christy. Christy, if you connected the 40 watt bulb
So when we solve this, we
directly to the
don't.
110, it would really be 40 watts. That bulb is not as bright as a 60 watt bulb, but it's pretty good. You can read by it. I need a lot of light. I like a 100 watt bulb for reading myself. But see, we have this lovely equation that goes like this, Christy. It goes. And look
So
at
when
here.
we're solving for this, we don't take into account that they're in parallel.
We're trying to find what the resistance of this bulb is. And that 40 watts is what you would really have if you connected it direct. Now, once we get its resistance, which we have, I figured it out, it's 302.5, then we're going to have to do parallel and series and all that jazz. But we're not there yet. You can't do parallel and series until you know what the resistances are. And to get them, that's what we're doing. We're getting the resistances. See this here, you take 40 watts, you take 110, and you square it, divide by R, and you solve for R, and what I got 302.5. Now, when I did this one, I'll tell you what I got. I got 60.5. Did anybody get 60.5 for R3? I'm listening for, yeah, there's a yes. Anybody else? There we go. Okay, now we're going to make Christy happy now. We now have the resistances. You have to jump, you have to go through this little dance first, and then you do that parallel jazz that we know and love. And so let's do it. First, I'm going to do this one here. I'm going to go 1 over 302.5 plus 1 over 60.5 equals 1 over the resistance of this parallel combination. And let me, as long as Christy, she's catching on to this. As long as she's talking to me, Christy, I want you to find the resistance of this parallel combination. Go for it, Christy.
I got 50.42.
Well, I'm not there yet, but I'm working on it. Boy, Jove, she's got it. It's 50.42 ohms. Now you see what you can do now is you can replace that. It's called simplification. Another name for that is the equivalent circuit. We could draw it over here. There's a little room. See what we've got here now. We have made this simpler. This here is 50.42. This one is 201.7 ohms. And Christy understands because she got the 50.42, but these are in series, so you have to add them. When you're in series, you know how that works. You just add them up. R1 plus R2 equals the total. So I'm going to add these up and see what I get. And I'm going to simplify this one more time. What I've got now is I've simplified it down to one resistor that's 252.1 ohms. You just add them, add those two. Okay, now we can get the current. Look here, if you have 110 volts and you have 252.1 ohms, you can get the current. V equals IR. Okay, find the current for me. Go for it. I've got the current. I know what the current is in this wire here. Of course, it's the same current in that wire, but now it's going to split here. We'll get to that later. And then it comes back here, and I know what the current is in this wire. What did you guys get?
0.436 amperes.
Yeah. Good going. 0.4363 amperes. It comes down here and hangs right around that corner. And it's still 0.4363 amperes. Now here, they're going to split. Part of the current will go this way, like that, and part of it will go this way, like. Now they'll come back together though, and when the current comes back together, guess what you'll have? You'll have 0.4363 amperes. Come down here, hang a right, go down this hallway here, 0.4363 amperes, and around she goes. By the way, when they split, see, R2 is 302 ohms and R3 is only 60 ohms. Which path will have more current, R2 or R3? Let me ask one of my excellent students here. How about Jacob? Unmute and say hello, please, Jacob.
Hello.
Hello, Jacob. This current, this 0.4363 amps splits. Part of it goes through the 302 ohms, and part of it goes through the the 60.5 ohms. Which one will get the most current, Jacob? What do you think?
Probably the one that goes through the less ohms.
Right. Good thinking, Batman. Isn't that what Batman, or isn't that what Robin says to Batman? And anyway, look here. This current is going to be the monster current. It's going to be the healthy current. And you're going to get current through here, absolutely. But I think you're going to get more current going through here because, gosh, 60 is what's that, 1/5? It's 1/5 of the resistance. It's kind of like, did you know the gravity on the moon is 1/5 the gravity on the Earth? So if you were going to go out for high jumping on the moon, on the moon high school track team, you'd really do great on your high jumping. But see, there's less resistance here. You get more current through there. Now, we've got to get our voltages. Guys, we're going to take a break here in a minute, but let's finish this problem first. I want to find the voltage here on this resistor. I know the resistance, it's 201.7 ohms. I know the current, it's 0.4363 amps. I've got a wonderful Ohm's law equation, V equals IR. I know the current, I know the resistance. I can get the volts on that. I've got a red pencil here, and I'm gonna mark in the volts on this R1, and I want you to find it.
88 volts.
Say that again, please.
88 volts.
I don't know. I haven't done it. I haven't done it yet, but I'm going to do it right now. I'm going to take 0.43.
That's what I got too.
I bet you guys are right. Times 201.7. Boy, Jove, we've got 88 volts. Good going. Proud of you. Now, these are going to have the same volts because they're in parallel. Do you remember when you're in parallel, the volts are the same? When you're in parallel, the volts are the same. Now, if that's 110 and you drop 88 here, what am I going to put in my red pencil here for the volts on here? They'll be the same. What's 88 from 110?
Are you gonna put 22?
I like it. It's 22. We're going to put 22 volts here, 22 volts here. Does 22 and 88 add up to 110? Yeah, it does. Good going. And now we can get those currents. Remember, they split. We're going to get them. Now, the volts here is 22 volts. The ohms is 60.5. So we can get the current. Look, V equals IR. If you know the volts, and it's 22 volts, and you know the ohms, it's 60.5 ohms, you can get the current through there. Do it. Let's get that current. Here goes. You take 22 volts, and you divide by 60.5 ohms. I'm just kind of running out of room here to write, but I'll scribble it down here. The current through here, that's this big current. We'll draw it big like this, is 0.3636 amperes. V equals IR. Now let's get the current through here. Now the volts is 22 volts, same as the 22 volts here. They're in parallel. The ohms is 302.5. V equals IR. We know the volts, we know the resistance. What's this current going this way? Plug it in. Let's say you take 22 volts and you divide by 302.5. Okay, I pushed the wrong button. At 22 volts, you divide by 302.5. Hey, I got my current through here. This current's not as big, guys. It's 0.0727 amperes. It's smaller. It's 72 milliamps. And my gosh, this is 363 milliamps. Okay, now there's one last thing to do, and then we'll take a little short 10-minute break, and I can go see what's in the refrigerator. We need the power. Now we have several lovely equations for power. There's some room right up in here. P equals IV. P equals I squared R. And P equals V squared over R. I don't care which one you use, they'll all give you the same answer. We need the power. Why don't I do that in maybe green? Here, I'll do the first one. I'll do the first one. I think I'm just going to use this one. I know the current, it's 0.4363 amperes. I know the volts, it's 88 volts. Okay, I'm just going to multiply them. Here goes. 0.4363 amperes, that's the current, times 88. I got 38.4 watts. Now that's it says 60 watts on it, but you're not getting 60 watts because you're sharing this power source with these other resistors. Does that make sense to you? I don't care, it does say 60 watts on the top of that bulb, because you've kind of diluted the energy here by sharing. You only get 38.4 watts. All right, now fine. I'll shut up. I want you to find the wattages on those two. Go for it. Well, I think I know the power on those two. Let me go to one of my students here. Daniel, unmute and say hello, Daniel.
Hello.
Hey, Daniel, do you have the power on either one of these?
Should I be multiplying by the 0.4363 still amperes?
No, Daniel.
Okay, then
The
never mind, hold
currents are not, they're no longer 0.4363. They split, remember?
Okay, then I
current
got
going-
7.9 or 8, I guess. Rounds up to 8.
You know what? I think he's absolutely right. I think this one here is 8 watts. Did anybody else get 8 watts for that one?
Yeah, I did.
Yay,
I
good
got-
going. Do I need to go through why that's 8 watts? You're okay? What's this one here?
1.6.
That's what I got. I got 1.6 watts. Now that thing says 40-watt light bulb, but it's only using 1.6 watts. It'll be very dim. In fact, I don't know if the filament will even glow. Do you remember in the lab we had some bulbs and they just kind of had a faint orange glow when the current was smaller? That's kind of what that looks like. That's a 40-watt bulb, but you're only getting 1.6 watts. Now look at here. This is a 200-watt bulb, but when you connect it up like this, you're only getting 8 watts. Do I need to show anybody how we got that 8 watts? Just speak up and we will if you want. Okay, well, the one last thing here, we'll take our break. I was going to show you, we've done this before. I need the room here. Let me make some room. Now we're going to make a little chart of power provided. And power used. Now the power used, they're in green. We got them. It's 38.4 and 1.6 and 8. There's 3 resistors and the total power, we got to add those up. You could call that 8.0 if that helps. I did that in my head. I'm getting 48 watts. Is anybody getting 48 watts when you add that up?
Yeah.
Okay, now that's the total power used. Now the power provided, the way you could get that, just use this equation here. We know the current. The current's the 0.4363 and the volts is 110. So what's 110? What's 110 times 0.4363? Boy, Jove. If you take 110 and you multiply by 0.4363 amps, I get, rounded off to 48 watts. Look here, we got 48 watts of power that we're providing and 48 watts of power that we're using. We don't need an answer book to check our work. We just checked our work. We know that is correct. Now we're going to take a 10-minute break, and at 7:15 we'll be back for more fun. So go stretch a little bit. Go stretch. I'm going to go see what's in the refrigerator, and I'll be back. 7:15. Take a break.
I'll be done soon. Okay.
Hey, Gabriel. What is the quietest sport? Well, welcome back, everyone. There's a problem like this on your test Thursday night. We better know how to do it. We did one like this in a lab, and I was pleasantly surprised. You guys were able to figure the currents and the voltages pretty darn good. Now you can't use simplification, or what's the other thing, equivalent circuits on this. You have to use Kirchhoff's voltage law. And remember, there's steps. The first step is you assign, well, you draw the circuit, and then you assign currents. And then the next step is you assign polarities. And then you write your KVL equations, and then you solve it. And the last step, will this show up? Yeah, barely. The last step is you check it, see if it's any good. Okay, let's assign these currents like we did in lab. Let's say that this one is I1, and this one is I2, and this one is I3. Then you can use Kirchhoff's current law and write this one as I2 plus I3. And this one you can write this one as I1 minus I3. And of course, when you come down here, this will be, you're back to I1 plus I2. Because if you add these together, the I3s cancel and you have I1 plus I2. So we just assign currents. Now I want you to assign polarities. I'll shut up for a minute and I want you to put pluses and minuses on these. Now if you screw this up, you'll never get it right. Resistors only have one way of doing it. I'll be quiet. Draw your circuit and assign polarities, and then we'll check them. Well, okay. I'm hoping you put a plus minus there and 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 a plus minus there. Did you do okay? I hope. And if you get that wrong, we got troubles. Okay, the next thing we're going to do is the KVL equations. Now there's not just one way to do this. You can do it a lot of different ways. One way is just to go around these triangles. Go around these triangles. There's one, and then go around this triangle here, and then maybe go around the whole thing. I'm going to shut up for just a minute, and I want you to try writing them. The thing is, there's different ways to do it, but they'll all give you the same answers. Go ahead, write your three Kirchhoff voltage law equations, and then I'll write mine, and we'll compare.
Will you remind me how you decide if it's positive or negative in the equation?
Oh, okay. Is that my friend Phoebe?
No, it's Christy.
I'm sorry, Christy. You have to decide which way you're going to go around the loop. Now, if you're going to go clockwise around these loops, that's different than going counterclockwise. but like, let's say I'm gonna go around this loop here, Christy, are you ready? Going from here to here, if you go from negative to positive, I would say that's an increase. If you go from negative income to a positive income, that would be good, wouldn't it? So it's plus. So you go plus 1 ohm times I1. See, what we're doing is V equals IR. This is going to be the volts getting across here. Now going from plus to minus, well, I'd say that's negative. If you had a positive income and it went to a negative income, that's bad. So we're going to go minus 2I2. And now we're going to go back to where we started. Now we're doing it clockwise, but you could have done it counterclockwise. Now going from negative to positive, well, that's good. So you're going from negative to plus. I'd make a plus 2I3 equals 0. Christy, did you understand that okay?
Yeah, I'm following.
Yeah, okay. All right. Here, Christy, you do this, go around this loop here and then go ahead and tell me. I'll write it. You tell me and I'll write it.
I did -2 ohms times I3. I started at the same point for the
Good for
bottom
you.
half.
Negative 2 ohms times I3. Keep going.
Minus 1 ohm times I2 plus I3.
I like it.
Excuse me.
I think
And
that's
then-
correct. Then what?
Plus 2 ohms times I1 minus I3 equals 0.
Excellent. Perfect. Now, Christy, as long as I got you on the line here, you can go around maybe the whole thing.
Okay.
Go for it.
-2 ohms I2
Okay.
minus 1 ohm I2 plus I3.
I like it.
And then I don't know the I1 plus I2. Do I multiply that by anything at the very bottom?
There's no resistor there.
Right. So that one doesn't matter, right?
There's no voltage change there.
Okay. And then it's just equal to -6.
Well, say if you're going around here like that, you'd say +6 equals
Well, yeah.
0. But if you want to have a -6 on the right, it's the same thing, right?
Yeah.
So we'll do it your way. It's the same thing. Those are all correct. Does anybody else have any problem with that? Now, if you have something different, that's okay.
I guess
might
I
have
just
gone
don't really
counterclockwise.
understand it.
There's more than
I
one
just
way to
don't
do
know.
this. Look,
Understand it.
does somebody need my help?
Yes.
Yeah, go ahead. I'm
I
listening.
don't. I guess you said clockwise versus counterclockwise, but on the first upper triangle,
Uh-huh.
we didn't really go clockwise or counterclockwise. We did positive and negative.
Well, now Christy went clockwise around the triangle. She went from here to here, and so from here to here, and from here to here. Now that's clockwise. Christy went around
Okay,
this
so
triangle.
what makes it -2I2 instead of +2?
When you go from we're going from here to here, and it's kind of like a mountain. If you're on a mountain and you're up here and you go down to here, you've just lost some elevation, haven't you? You've lost some energy. To go from here to here, you've lost some voltage. See, voltage is energy. And so it's -2I2.
So then what made the I3 positive? in that scenario.
What made the I3 positive? This one here?
Yes.
Oh, okay. Well, here we're going from negative to plus. Here we're going up the mountain from negative to plus. It's like you're negative, here's plus, you got a higher elevation, you got higher energy. This is negative, this is plus, but we're going from here to here. We went up the mountain, so it's plus. Plus,
Okay. Thank you for breaking it down for me.
anytime, just thank you for asking. And now we could have done this about a dozen different ways, but they'll all give you the same answer. Okay, but now the next step is math, algebra. You got to clean these up and make these pretty. This first one's fine, but this second one we're going to have to doctor up. I'm going to write this as 2I1. See the 2I1? I'm working on this one here. And there's a negative 1I2. And now on the I3, I got negative 2I3 and negative 1I3. That makes negative 3I3. And negative 2I3, I think that makes negative 5I3. You can double check me, make sure I don't goof that up. Let me rewrite this first one. This is 1I1 minus 2I2 plus 2I3 equals 0. Now we're going to do the last one. Now there isn't any I1, so that's 0 I1 minus 3I2 minus 1I3 equals minus 6. Now stare at that, and if I made a mistake, speak up. Now what are we going to do? Well, what I'm going to do is I'm going to get my calculator here, and I'm going to turn it on, and I'm going to push a button that says simultaneous linear equations. And then they want to know how many. Well, there's 3 of them, so I'm going to put in a 3. And then it wants the coefficients. So I'm putting them in. That's a 1, minus 2, 2, and a 0. Then I'm going to put in a 2, and a minus 1, a minus 5, and a 0. Hey, I'm having all the fun. You do it. I'm gonna do it. I want you to do it. And when you get through, tell me what I1, I2, and I3 are. I'll be quiet and let you get out your calculators. I'll give you a couple of minutes if you need it. Go for it. Well, let me call on somebody and see how we're doing here. How about my friend? We'll pick on Zach again. Zach's a good sport. Zach, did you get your calculator to spit those answers out yet?
Yeah, I got 1.5, 1.928, and 0.214.
I did
No,
not get those numbers.
I didn't get that, Zach.
Yep.
Now that doesn't mean that I'm right and you're wrong yet. Somebody else. What? Give me a,
2.4, 1.8, and 0.6.
That's what
that's
I got.
what I got. So Zach, you just learned a valuable thing. You got to figure out how to do that. Something bad happened. I don't know what happened. Probably pushed the wrong button somehow. Now I want to know if anybody else got that. There's a couple of us. Anybody else? I hear. Give me an uh-huh.
Uh-huh.
Yeah, there's one.
Uh-huh.
There's one. I bet those are right. Okay, now we solved it. We went through the steps. We assigned currents. We assigned polarities. We did the KVL equations. We solved it. Now we're going to check it. We're going to find out the voltages on every component. Here goes. We know what I1 is. It's 2.4 amperes. These are in amperes. And we know what I2 is. It's 1.8 amperes. While we're at it, why don't we get I2 plus I3? That would be, what's 1.8 plus 0.6? Would that be 2.4? I think it would.
Yes, sir.
I think it would. I think what we got going down here is 2.4 amperes. And what we have here is 1.8 amperes. And this one here is 2.4 amperes. Now let's see what this is. I1 minus I3. Well, that'd be 1.8 amperes, wouldn't it? I think this is 1.8 amperes. Now, when you add those together, what's 1.8 plus 2.4? 4.2? Are you guys getting 4.2 amperes going through here? 4.2 amperes. 4.2 amperes. And it splits. If you add these two up, does it make 4.2? Yeah, it does. Hey, we got all of our currents. Now let's get the voltages. Let me get my red pen out here. Well, why should I have all the fun? You do it. You get the voltages everywhere, and I'll shut up for another minute. Go ahead, get the voltages. I can do some of those in my head. Well, I did all that. Now for this one here, I got 3.6 volts. Tried to do that in red. I don't know if that showed up. This one here, I got 2.4 volts. This one here, I got 1.2 volts. Now the 2.4 and 1.2 add up to 3.6. Yeah, well that's good. That worked pretty good. Now for this one here, I got 3.6 volts. And for this one here, I got 2.4 volts. And of course, I got 6 volts for that one.
Wait, the only one of yours that I got different is the bottom right. You got 2.4 and I got 3 volts.
Okay, now
Because it was.
I2 plus I3
Mm-hmm.
is 2.4 amps. And if you take 2.4
Oh.
amps times 1 ohm, you
Yeah, I
get
just can't math.
2.4 volts. You okay?
Yeah, I'm good. I don't know what I did wrong.
Yeah, it's hard to know when you get lost. It's hard to know. All you know is you're lost. Okay, now let's get the power. Okay, now there's 3 equations for power. And so you can use any one of the 3, I don't care. Why don't I put those in green? So I'm going to shut up again for a minute. I want you to get the power on each one. I'll be quiet. And we're going to get the power now. Well, I think I have all the powers now. Let me write those down. It's kind of messy. I got 6.48 watts on that one, and 5.76 watts on that one. I haven't done that one in the middle yet. Let me do it. I'm getting 0.72 watts on that one there in the middle. And on this one, I'm getting 5.76 watts. And on this one, I'm getting 6.48 watts. Now for the battery, I got 25.2 watts. Now, does anybody need me to go over any one of those? Hope you can read that. This is supposed to say 25.2 watts. Does anyone need me to go over any one of those?
Could you just write the base equation for watts?
I tell you what I did. I used the same equation for all of them. I just went P equals IV. That's all I did. I know the currents on everything. And I know the volts on everything. I just multiply them. That's what I got. Did you need me to do any one particular one?
No, sir.
Okay. All right. Well, let's. Anybody need my help on that? Because what I'm going to do now is the last step here. It's called checking your work. We're going to do that now. But just speak up if you have a question. I need the room here, so I'm going to make some room. There, I made some room. And we're going to have power provided and power used. Now the power used is, there's actually 5 of them. There's 5.76 watts, 6.48 watts, 0.72 watts, 6.48 watts, 5.76 watts. Now the power provided we have is 25.2 watts, if I did that right. Now I'm going to add these up, and if it says 25.2 watts, we will have checked our work. Add them up. Boy, Juve, I'm getting 25.2 watts of total power used and 25.2 watts of total power provided. Do I need to write out in detail anything? Just ask and I will. Just ask. Well, nobody's asking me anything. Okay, well, we got time for one more topic for sure. According to my watch, I got a half hour with you guys. And you paid your money, right? So let's give you your money's worth. We're going to talk about internal resistance of batteries. If you're happy. If you understand all this, I'm going to erase it. We're going to talk about internal resistance of batteries. Okay. Go
Not
ahead.
this one, but the first question we did earlier that you said would be on the exam.
Yeah.
Was that 10-57?
Let me tell you, I'll tell you just one tiny second here. It was the very first problem we did tonight was 1051.
1051. Thank you.
Yeah, anytime. Okay, well, we're going to say goodbye to the KVL stuff. Bring your fancy wancy calculators that does 3 simultaneous linear equations. Make sure that the batteries are fresh. Make sure you know how to do it. I think, Zach, get your book out and figure out how to do that right, Zach. Okay? I want you to do good.
But yeah, do the arrows always point like that?
The truth of the matter is you can point those arrows a different way. Is that my friend Jacob? Is that who that is?
Yes, sir.
Jacob, I think on the test, though, I'll give you the directions so there won't be any confusion, okay?
Okay, sweet.
Yeah, but you don't have to do it that way. The only thing is if I drew that arrow going the other way and I solved it and got my answers, I would get a negative, you know? And that would tell you that, uh-oh, it's going the other way.
So we should always get a positive value.
If I'm not being tricky and trying to fool you guys, the answer is yes. But
All right.
sometimes I'm tricky and I try to fool you, but I really shouldn't. That's not very nice. Okay, now let's talk about batteries. Let's suppose I have a 6 volt battery. You guys have all seen these in the lab, that we have those. They have, strangely enough, the positive is on the end there, and the negative is in the middle, and it says 6 volts, but if you put your voltmeter on there and measure it, if it's a fresh, brand new battery, it might say 6.2 volts. 6.2 volts. If it's not connected to anything. But now I tell you what let's do. Let's connect it to something. We're going to connect it up here. We'll come over here. And we'll put a resistor in there. So suppose I put a 2 ohm resistor in there. And then I measure the voltage. I'll get my voltmeter. And I'll measure the voltage. You know, it has a red and a black lead there. I forget exactly where they go, but we'll put the red lead there. See, that's the positive one. And we'll put the black lead. Not sure where it is. We'll just say it's there. Put the black lead there. That's the negative end, right? Negative, positive. You want to put the positive lead on the red one. And let's say when you measure that, it doesn't say 6.2 volts. Let's say when you measure that, it measures 5.88 volts. Well, this battery has an internal resistance. And it's given by a little R there. It's called the internal resistance of the battery. And this is all explained in your book on page 440. And 441. Well, and 442, there's several pages there, but you could read it. Now, I'm going to shut up for just a minute here, and I want to see if you can figure out what it is. See if you can find the internal resistance of the battery, and then I'll help you with it here after you've tried to do it yourself. I think you'll learn more by struggling. See if you can find the internal resistance of your battery. You're free to look at page 440 if it'll help you. Well, maybe we should go ahead and show you that in case you're rusty on that or you've forgotten how to do it. It would be very helpful to draw a schematic of the circuit like they do on page 440. What they did there was they drew your battery, and you have to recognize that the battery includes the internal resistance, R. See, this is a 6.2 volt battery, but it has this internal resistance. And here's your load. They call this the load. And this particular load is 2 ohms. And we found that the voltage on that 2 ohms is 5.88 volts. Let me put that in red. I think this is easier to understand than this other diagram. Okay, we've got our volts. I wish that would show up darker. 5.88 volts. There we go. And now see, we can get the current in the circuit because V equals IR. Ohm's law for resistors. And you have the volts on this resistor and you have the resistance. So what's the current? You tell me. I'll ask one of my excellent students here. Stephen, let me pick on you again. I've only picked on you once or twice tonight. Stephen, unmute and tell me what you think the current is in this circuit.
I'm getting a 0.3401.
Not what I'm getting. Yeah. Look, if you know this V is 5.88, and you know that this resistance is 2 ohms, solve for the current. Do it again, Stephen. You did something wrong. I don't know what you did, but you did something wrong. Well, what do you get for the current, Stephen?
If I do it the other way, it's 2.94.
That's correct.
Okay. I flipped my numbers.
Oh, well, you learned something. It's 2.94. What are the units, Stephen?
Amps.
I'm sorry, what?
Amperes.
Yeah, there you go. Good going. So we now know that we have 2.94 amperes, and they're going this way. 2.94 amps. They go around here. 2.94 amps, and they go round and round. Now we're going to use Kirchhoff's law around this loop. Let me make a little. I need the room. If you go around this loop, you got 6.2 positive from negative to plus. You got minus IR, which is 2.94 amps times that little r. And then you have, I need the room here, you have minus 5.88 volts equals 0. Hey, look, Kirchhoff's voltage law, I just went around this loop. You go up 6.2, you go down 2.94 times R, minus 5.88 volts. See, this is plus minus, equals 0. Now solve that and give me the internal resistance of the battery. Go for it. Well, I did that, algebra students, and I got an internal resistance of the battery. I got 0.1088 blah, blah, blah ohms. And if you got that, I want to hear an uh-huh.
Uh-huh.
Yeah, there's one.
Yes.
Yes, yeah, excellent. We now know what the internal resistance of your battery is. It's 0.1088 ohms. So we could write that in. We know what it is. It's 0.1088 ohms. Now, I want to show you something. We got 12 minutes, and this will be kind of interesting. Some of you might know about impedance matching. Some of you might have boom boxes or whatever, or audio blasters in your cars. I know people in my neighborhood do. They go by in their cars, and I hear boom, 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 boom. Drives me nuts. The whole house shakes. And what they've done is they've matched their speakers with their power source on their whatever they call their thing there. And I'm going to show you about impedance matching here for just a minute, if I can find some room. There's some room up here. What we're going to do is we're going to find the power in our load. And we're going to have the load. This particular load is 2 ohms. And we're going to find the power in that load. Now you have 3 equations. You know everything there is to know about this resistor. We know it's 2 ohms. We know it's got 5.88 volts. We got 2.94 amps. So what is the power in that load? Go ahead, I'll shut up. Find the power in that load. Let me ask one of my wonderful students what they got for the power. Phoebe, unmute if you have it, and tell me what the power is in that load. What'd you get?
I'm still doing it. Oh, 17.3.
I got 17.3. And what are the units?
Watts.
A good going.
Watts.
17.3 watts. Good going. Now let's put some different. We already got this resistance. I can erase that for a minute. Let's see what you'd have with different loads. See, you have to match your speakers to the driver, the output. I forget the name of it. Suppose you had a 1 ohm load. If this was 1 ohm, everything's different, guys. If that's 1 ohm, now this won't be different. That internal resistance is the same. That 6.2 volts is the same. But see, if you make this 1 ohm, that changes the volts and it changes the amps. So here, let me find the new the current. The new current through here would be the 6.2 divided by the 1.1088, if that made any sense at all. And I'm getting, with a 1 ohm load, I'm getting 0.1788 amperes. And I'm getting voltage. Let me put that in red. If you have a 1 ohm load and you have 0.1788 amps, then V equals IR, you get 0.1788 volts.
How'd you get 0.1788 amps?
Oh, thank you for asking. I appreciate you speaking up. The total resistance here, they're in series. It may look parallel to you, but it's not. This is a series circuit. It goes around and around. And the total resistance is 1.1088. You'd have to add these two. See the 1 and the 0.1088, you have to add them. That's the ohms, and you have to divide it into 6.2 volts. If you'll do that, you'll get 0.1788 amps. Do it. Do you understand that this is not a parallel circuit? It may look like one, but it's really a series circuit. They're all in series, aren't they?
Yeah, but I think you're getting the wrong number.
Hang on a minute. You could get a thank you point for this. 6.2 divided by 1.1088. I didn't get that. I think you're absolutely right. I think I'm wrong here. Now, just a minute. If you take 6.2 volts and you divide by 1.1088 ohms, you get 5.592 amps, right? And I really appreciate you. Who was that? Was that Zach? Is that Zach? Huh?
Yeah, yeah.
Zach, I'm gonna give you a nice big thick thank you point. I think what we have here is 5.592 amperes. Zach, is that what you got?
Yeah, that's what I have.
Yeah, okay. And so with a 1 ohm load, you have I don't know what I did, Zach. I pushed the wrong button. You get this amount of voltage. And so now we can get the power in a 1 ohm load. You'd have to multiply these two, and here's what you'll get. I'm getting 31 point, we'll round it off to 3 watts. Hey, look, we're matching the load, or for the guy in the car, the speakers that you get, we're matching it to his power source. And look, you're getting 31 watts. Well, that's an improvement. That is, if you like that obnoxious noise, if that makes them happy. Well, let's try another one. Let's go down to 0.5 ohms. And let's see if I can do this right. We got time. I got 4 minutes left in class. I'm showing you something here about matching your load to your source. That's what I'm trying to show you. Now, if this is 0.5 ohms, if that's your load, then what will be the current then? Well, I don't know. And to get the current then, you'd have to go 6.2 volts, and you'd have to divide by 0.6088. I didn't lose anybody, did I? So you'd have to add that 0.5 and the 0.1088. And here's what you'd get for your current. Your current will be you'll get 10.1, I don't know, 18 amperes of current. I hope I didn't lose anybody. And now for the voltage on your load, V equals IR, if that's the current and that's the ohms, well then multiply that by 0.5 and you get 5.09 something volts. Now we can get the power. Multiply your current by your volts and we'll get the power. Here goes. Well, looky here, 51.8 something watts. We are finding that we can get more power. And you wonder, well, I wonder what's the maximum power that you can get? I'm running out of time, so I don't have time to show you why, but I'll tell you this, the maximum possible power that you can get is if the load matches the resistance of your source. If you, we don't have time to put it in right now, but if you have a load of equal to the resistance of your source, you'll get the biggest possible, you'll get your maximum possible power, and they call that impedance matching. And some of you might know quite a bit about that already. Well, it's sad, but our time has come to an end. I hope you've had a good time. I have. Now, any last words before I push this red button? Here's your last chance to say anything. Until when? Thursday at, in the lab at 5:30 for your test. Yeah. I'll see you Thursday. Okay, well, I'm going to say bye-bye. Bye-bye, students.
Bye.
See you Thursday.
Bye.
Bye. See you Thursday.
Bye.